All right, ladies and gentlemen, welcome. This is the third week of Kinetics. We've got a test next week, and we'll try and finish this up with two lectures. This is going to be this week, and this is going to be the first one. And the goal of this is to understand how to calculate concentrations using rate constants and time. So we're going to talk about some plots and some how we figure out these concentrations, because this is going to be on the test. You will get a set of set of problems today with this lecture, and hopefully this will become clear. Now, we had, according to the simulation, three different type of plots. We had zero order, first order, and second order. And what we have is that with the first order, we're looking at the plot of, this is y. Oh, my pen is not working today. Okay, let's get this. There we go. Y is equal to mx plus b. And with the zero order, there is no x. It's just y. So we get this. The rate order is related to just the order. And so when we look at rate versus time, this is going to be the concentration versus time. And we got a straight line. And where this is the rate. Now for the first order reaction, it's going to be 1 over a, logarithm of a. That's a straight line versus time. And this is second order. And so this is 1 over a versus time. And this is going to be a straight line going actually this way. Now, I want to point out is that, this is 0 or 0th. This is first. And this is second. Now, there is another second that we have, that's rate, is equal to minus k times a times b. And this type of calculation is going to be a little bit more hard to figure out the concentrations of each one. This involves a little bit more calculus, and we will not do this in this class. Just be aware that's another type of second order reaction. So we're looking at this. We have one of these three, looking at just one concentration being affected, either zero, first, or second. Now, to get what we need, we actually have to use calculus. And here are the results of calculus. If you know in calculus, you can actually calculate these equations from the equation of the line. That's fine, but this is what we need. This is what we're looking for. This one and this one, you should be able to do without any problems. I want to point out that AT is equal to the concentration, is read as the concentration at time t, and A sub 0 is equal to concentration at time 0 seconds. And this is a little bit changed from if you had me in physics. We usually go initial and final, but this is another way of saying that, and this is the terminology in kinetics. And now I know you guys are going to go nuts over this. It's a lot to know, a lot to memorize, but just write this down. This is chemistry and physics have their own language, so it's something you need to be aware of. So we're going to look at calculations looking at first order reactions. So we're going to look at this and how to solve these type of problems. Again, this one and this one you should already know. Now, here's one thing we need to realize is that K can be either in seconds to the -1 or minutes to the -1. So you need to convert time you need to convert time to those units, depending upon what this is. So it's something you need to be aware of. So what we have is we're looking at the decomposition of H2O2, hydrogen peroxide. Here's my initial concentration. This is equal to A sub 0. Here's my rate constant is in seconds to the -1. And we have a first order reaction. So you need at least this three information to figure out how to do the rest. And from this, we can find two things. One, find the concentration of hydrogen peroxide after 4 hours. So we need to convert 4 hours to seconds. So 4 hours, level 1, 60 seconds per hour, 60 minutes for an hour, and 60 seconds per minute. And so you get 14,400 seconds as the time. Then the second part is how long will it take? We're looking for time to drop 2.12 molar. So we've got two things we're looking for. And this is going to be the hardest one. This is actually easy to calculate. We're going to go over both to see how you do. So let's go to the equation. Log of a sub 0 over a t over a 0 is equal to minus, what was it? Minus kt. T, remember, is 14,400. K is going to be 1.8 times 10 to the minus 5th. And a sub 0 is going to be, I believe it's 0.3. Now, this means the concentration off, so I can leave off the units. So we need a sub t. So what we're going to do is, there's a couple ways to solve this, but what I would do is take this fraction, a sub t, put in 0.3, then take minus k times 10 to the minus 5th times 14,400 and multiply these two together. You should get a negative 0.2592. I want to keep all my units for the time being, don't round yet. And this is equal to the log of the concentration of AT over 0.3. Now I'm going to raise both sides, e raised to this power, e raised to this power. So what we have is this fraction a sub t over 0.3 is equal to e to the minus 0.2592. Therefore, a sub t is equal to 0.3 times e to the minus 0.2592. And I'm going to solve concentration at my time. So this number here is 0.77 roughly times 0.3, and you should get a value of 0.232 molar concentration. So that is the answer for the first part. All right, so I'm going to erase all this because I want to use I'm still going to use this equation for the next one, but we don't know time. So we don't know time in this, and then a sub t is equal to 0.12. Now this is going to be an easy calculation because we're going to use this. So the log of 0.12 divided by 0.3 is equal to minus 1.8 times 10 to the minus 5th times time. Again, there's a couple of ways to solve this. Let's go ahead and do the logarithm first. So the natural log of 0.12 divided by 0.3, it's going to give me a number of minus 0.91629, and that's equal to minus 1.8 times 10 to the minus 5th t. Divide both sides by minus 1.8 times 10 to the 5th. And then we're going to get seconds by itself. Excuse me, time is going to be 50,905 seconds. Now, let's put this into hours. So take this number. If you want to leave it here, that's correct. But let's put it into something that we can actually have some type of meaning to. So 1 hour is to 3,600 seconds. So if I divide this number by 3,600, I basically get 14 hours and 0.14 hours. So that is the time it takes to decrease by 1/3, almost, from 0.3 to 0.12. Now the next one we're going to look at is, I've been kind of getting over this. We did this in in class. We're going to look at this one. I'm going to use this equation to solve the problem. And so what we have is activation energy. We're given a rate constant at a certain temperature. 4.58 moles to m to the minus 1 seconds to the minus 1 at 300K. At 400K, the rate constant is this to determine the activation energy. And so what we're doing is we're going to take, so we have this equation, log of K2 over K1 is equal to minus EA over R times 1 over, and this is going to be, so let's take 300 as T1, so 400 is going to be T2. Let's go T2 minus 1 over T1. Let's do it this way. So T1 is going to be 300 Kelvin. Therefore, K1 is going to have to be 4.58. Keep the temperature and the rate constants together. So T2 is going to be 400 K, while K2 is 8.45. So we're looking for this guy. And now R is 8.314. So let's go ahead and plug in the numbers. So log of K2, K2 is 8.45 divided by 4.58 is equal to minus EA over 8.314 times 1 over T2 is 400 minus 1 over T1, that's 300. All right, so we're looking for EA. And now, this is one thing I want you guys to do. Instead of moving everything back and forth to isolate EA, we're going to do this in parts. And this is how I would do it to keep it simple. Solve this first. So you got 8.45 divided by 4.58. That's giving me 1.84497 something. And just take the natural log of my answer. And I should get this is 0.61247 minus EA over 8.314. Now I'm going to take 1 parentheses 1 divided by 400, close parentheses, minus 1 divided by 300. I'm going to get this number. Now, what I see, and you guys are forgetting that you cannot subtract denominators. You got to get this to a common denominator. So 1 over 400 minus 1 over 300 is not 1 over 100. That is not correct. Nowhere near. So don't do this. All right. Guys, this is a college class. I'm expecting you to know how to do all this. And the AC and the AP test will also recognize that. So you take this number, multiply by this number, divide by that number. So over here, minus EA is equal to 8.314 times 0.61247. And then divide by negative 8.33 times 10 to the minus 4th. Negatives cancel, so EA is equal to, sorry about that, I pressed the wrong button. I'm always doing that. 8.314 times 0.61247, and take that number, divide by 8.33 raised to the minus 4, and you should get an activation energy of 6,113 joules per mole. And that's how you solve that. Now, if you're looking for what the right constant is for a certain temperature, other than these two, you just use T1, the other temperature for T1 and T2. I'm going to leave that for you to solve. And this is long. Remember, if the rate constant is doubled, K2 is equal to 2K1. So you got this logarithm. 2K1 is K2, K2 over K1. That's also a natural logarithm of 2K1 over K1. These cancel, so you have the natural logarithm of 2. So when looking for half-life, whoops, I forgot the 1 over 2. So AT is equal to 1/2 of A sub 0. This is what we mean by half-life. We're losing half the concentration. And again, units, make sure you're matching the rate constants. This has been a long lecture. I'm tired. You're tired. You tired of hearing me? Have a good day, folks, and we'll talk to you later.